Okay. Uh, Kevin, Prof, if the OS have protection against illegal address access buffer overflow, doesn't work anymore. Yes, with data execution DEP in place, it doesn't work anymore. So what we see in this format string attack is, even if DEP is there, even if we cannot execute something in the stack, we'll see a way in which we can still make it work, right? So what user permissions do you get? You get the user permissions that is allowed in that particular user level. So if you are getting a shell, so there are shells with root privileges, but mostly what you get is what that particular, because the shell is within that user, you're just spawning a shell within that user. So usually you'll get the same user privileges as that user, not root. Okay. One question first. I'm doing YouTube live for the first time, so can you hear me properly? I'm not getting any answer, so I'm worried that you can't. Oh yes, good, great. So let us get into the format string attack now. I don't want to make you wait till 12. So let us get into the format string attack. So we have seen buffer overflow. Now the next one is format string. So let us start that. Give me 1 minute. Okay. So same as previously, there are two programs. First one, a simple one. You can look at example, copy this code from the lab manual, where it has two things basically. There is a secret string. This is a secret which is in the stack of obviously, and there's a number n equal to 10, and it prints the command line argument argv and just prints that. That's all. At the end, it will also print the value of n. So when I run this program, what I get is, it gets something like this. Say hello. It prints hello and it prints 10 because 10 is stored. It prints a string and it also prints the integer 10, integer that is stored in n. So how do you compile this? You compile is using the using the options that I have given in the lab manual. So these are the, this is how you compile it. GCC minus m preferred stack boundary 2 minus m32 example 1, etc. So if you look at here, there is some flags. Look at what those flags are. That is something which you have to do as a homework. Identify why these tags are used. But I have changed the no exec writes flag. So this one, even if I put something onto the stack, I cannot execute it. Okay. So what we are going to, so both, there are two programs that we will work with in this format string attack. In both cases, we won't what is it called, we won't we won't be having execution rights on the stack, but we'll finally find a way to get shell even without that. Okay. So have you, I assume you have copied the program. I will give a minute for copying the program and compiling the program. Okay, so if you have copied it, let us see what we can do. with this program. uh, okay, so example 1, when I type hello, it prints hello and 10, right? What happens when I print example 1 %x? It prints something gibberish. It looks like an address location, right? So it looks like an address that is stored in stack. Okay, so let me add one more thing. I'll put a dash and add %s. Look what just happened. I just got something that is in the stack, which is, this is a secret. If this is %x, I will see another address. So this address is basically the address to the second element in stack from where buffer is stored. So buffer, and then there's a %x, there's another %x. The second element in the buffer, in the stack, which is the address location to the string, this is a secret. So if you look at the program, vim example1.c, what do you, okay, one has to be, if you look at this program, you can see there's a string which is a secret, which is in the stack. There is n, which is in the stack. Then there is a buffer arg1. This is something that we control, right? So this one, when I put printf argv like this is the problem that creates string, a format string attack. When I put argv like this, what happens is that %x, the first %x will take something from the stack, which is gibberish. I don't know what that is. The next one, fortunately for us, is the address to this particular string, and prints that. Very simple attack, but very effective. So with that, our first format string attack exercise is over. Now something which you want to do at home is, like one of you have said when we were having our lecture earlier, that you can use this to crash the stack, crash the program. So try to craft a format string attack to crash the program, to see if you can crash it or not. It is possible, and that is something that you do at home. Now let us go into the next step, the next for advanced format string attack level, where we are trying to get a shell even when there is DEP, even when there is data execution protection, which is enabled. Okay, for that, let us consider another program. Let us consider this example2.c. oh, sorry, not example 12, example 2.c. English is not my best friend. Example2.c. We have this simple program with how many lines? Like 15 lines, but mainly three lines. It has 3 functions. There's a buffer b of 128 element long, byte long. Then string copy, whatever argument is there, I copy that into the buffer b. That is not, so there is a buffer overflow problem here, but we are not going to exploit that. We're going to exploit this printf b. I can print b as I want. I can print this as I want. That is what we are trying to exploit. So I put format strings here so that I can exploit it in some way. And then there is a naive looking program, str function strdup b over here. It also uses b, and it just duplicates the string. Okay, this program, how can we get shell from here? So I will give you a minute for you to copy the program from your lab manual, store it in a file called example2.c, compile using the same set of instructions that I have given, the GCC flags that I have given earlier. Compile it, and once you are ready, we will go forward. We'll give you a minute for that. Okay, assume I've done that. So let us get into the attack mode now. So first step first, example to what if I do this, this just example 2 hello, oh, example 2 hello, it give me hello, right? Example 2 hello, instead of hello, if I put %x, I get two things from the stack. I put %x, %x, I get 3. Okay, now our front is a because that is what we can, how we can identify where exactly the buffer is. So you can use other identifiers as well, because we did a for the buffer overflow, and we all know what is the hexadecimal value for a. Let us go with a. So I'll put some a's and then a few b's to differentiate, and then I'll put a %x and see what comes. So it print the buffer, so that is what it's doing, it's printing the buffer. And then after it prints the buffer, it the %x, it prints the buffer, and then the dash, and then the %x is popping out or accessing the first value in the stack after the buffer. So let me see if I can get more values, and if it makes any sense. I'm getting more values, but if you look here with %3, with 3 I can get 41414141. What is this 41414141? This 41414141 is basically a. So I am accessing, what am I accessing here? What is this? This is basically where the buffer is, correct? So I'm writing this a b, and this location where a is stored is accessed from the stack. So just to make this a bit more funnier, I'm adding some junk thing as of now. We will see why these junks are added later. I'm adding sh semicolon hash. Okay, why I add sh semicolon hash? Some of you may have guessed, because I'm going to run a script where I need to spawn a shell. That is why that sh is there. But right now these are random alphabets, random literals. There is nothing special about these things. Okay, so of course, to make it as a buffer I need to put, because semicolon is there, I need to use this. But now I lost 4141, so I need to put one more %x probably. I should get this, and I can get 41414141 over. Okay, so you can see the AAA in the format string is written onto the stack and can be accessed through the format string. So this buffer is written onto the stack. This whatever the string is, it is written onto the stack, and at the same time, with this format string, I can access this AAA from the stack using this format string attack. So we now know that the fourth element in the stack from the format string is where AAA. So where is this located in the stack? This is located as the fourth location in the stack. And there is something which is very handy here in this format string attacks. Format strings, there's a option in the printf. If I want the fourth one, I can just use %4x. Oh, sorry, not just 4x. I need to put, if it is in the C program, I just need %4x, but here I need to put here $4, and I can directly access. I don't have to put %x to access this thing. I can just directly put %4x to go directly to the fourth one. If I want the third one, I can put 3x. So 3x will be very similar. This is 233, and it should be similar here. 233 B6 873. or 233b6873, you can access directly. Okay, give me a minute. Is there any comment here? Someone asked, will I upload this portion to Excite? I will. This will be in this channel. If I remove this from this channel, then I'll record this and put that in Excite. Okay? If I am not removing it, for instance, the last lecture I haven't put up in the Excite, but you have the links and you can access that. So probably at the end of this a few weeks I may remove it. If I remove it, then I'll put that thing on the learning management system, LMS. Okay, so you can see, directly go to that address location. Now what's the next step? So we are going to use our main arsenal, which is %n. Remember what I said about %n? If I use %n, I can write onto the variable, right? How do I write onto the variable? Sorry, 1 minute. Okay. How do I write onto the variable? I can show you with a simple example that I have shown earlier. So this program over here, what does it do? It does 1 2 3 4 5 6 7 7. It prints that, and then %n and %a. So what it does is it takes all the numbers that is printed just before it sees %n and store that into the address location of A. Okay, so if you run this program, what we get is this: 1 2 3 4 5 6. The value in A is 7, so that value is stored in A. So if you look at the program again, even if I put A as 0 here, and then compile this, I still get the value of A as 7. Okay, if I change this to, say, add more things, 2 more characters, let me put 2 more characters, say 2 dash. Okay, it should print 9. See, so %n gives you that power. So we are using that %n. So if I put $3 $x, I'll get the third element. Instead of this, if I put %3n, what happens is all these things: 1 2 3 4 5 6 7 8 9 10 11 12 13 14 characters. This 14 will be stored in this address location, and it mostly will crash because this address location is a junk address location. So that is exactly what happened. It just seg faulted, right? So we'll go back to our friend GDB. So GDB example.2 to make us okay, and we will get the same seg fault, but with the run. I give the same sh semicolon hash AAAABBB for, and so we are trying to write onto 414141. It will mostly seg fault. Yes, 6 seg fault, segmentation fault. We get the segmentation fault. But let us see what happened at the segmentation fault port. Okay, so we will look at EAP. Okay, let us see what is there in the EAP. So as we discussed earlier, EAP is extended instruction pointer. We are looking at the instruction pointer where the set right now, and the instruction pointer we have right now is this, as at this location, and the instruction at this location is this: move %edx %eax. So what is happening is the instruction transfers values from edx, okay, whatever value is in edx, to the memory location stored in eax. So whatever is so this is a pointer in EAX. Whatever is stored in EAX, whatever address that is, to that address location, whatever value is stored in EDX is transferred. So let us see what do we have in EDX first. Okay, let us just print EDX and see what we have in EDX and what we have in EAX, EDX. Sorry. So EDX we have E. What is E? E is 14, right? So look at the number of literals that we gave. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is what we have in EDX. So it is trying to store 14 where in EAX. So let's see what we have in EAX. So it is trying to store 14 at the address location 414141. It is not trying to store 14 in EAX. It is trying to store 14 at whatever is in EAX. So 4141. So it is trying to store at address location 414141. This EAX 14. Okay. So that means I can write. Now we know that it is possible to write into a memory address by manipulating the string. The segmentation fault happened because of the invalid address location 4141. So if we give a good correct address location here, we can write whatever we want in there. Okay, we're almost there to get the shell. So to get the shell, we need something else. So we need to look at the program and we need to make this program look a bit more, manipulate something based on the program's logic. Okay. So let me open the other. Okay. Let me open the program again. CD format string ls. .c. Sorry, I don't know if you have asked any questions. Okay. So if you look at this program, there's this function called strdup, and strdup also uses b like as a input. So remember I put sh in the beginning. There's a reason why I put sh in the beginning of this string. Okay, so because this is b, this is the b that we are going to give, sh semicolon hash. So instead of this strdup, when this strdup get executed, if we can run system sh, then it becomes system, and here b it becomes sh semicolon something blah blah blah. So the rest hash, because of hash it is commented out. I don't care what the rest is, but I get system sh. If I type system sh, if I have system sh running in C, I get a shell. So my aim now is to make this strdup look like system, or make it, convert it into system somehow. How can I do it? Step 1 is to find where strdup is stored. Where is strdup? So strdup is somewhere the memory location where I can find it using global offset table. So what is global offset table? Global offset table is something which is used by a program at compile time to determine the location of the functions used from external libraries. So strdup is a function that I am using from an external library. So where exactly this strdup is located, that I can find from global offset table. And how do I find where is that location? By using this simple command called obj dump. So if I do obj dump example -r example.2 example2, I will get the global offset table, and within the global offset table I can see strdup, right? So this is where strdup, this address location is where the address of strdup is stored. So imagine strdup is at location 1000. So if you go here and look at 804 A004, what is written here is 1000. So this points to strdup. Okay, so it basically, let me show you this screen. This is address location 804 A004, that points to the function strdup. What we are going to do is we'll manipulate this address location and change that to system. So we saw that at 41414141 we are able to write something. but instead of 414141, we'll give 804A004. So in this address location, write something. What are we going to write? We are going to write the location of the function system. Okay, so that is our strategy to get system function, getting system function executed instead of strdup. Okay. So let us try doing that. So we found 804A004. Write this address location somewhere. We may need to use that pretty soon. Okay, so let's go back to GDB now. GDB, example 2, and I will run this particular code. Python -c print sh semicolon hash. Instead of a, what I did is 0804 A004. So this address location 0804 A004. That address location I replaced that with instead of a. Okay, the rest is same. b %4 $n. So now let us see what happens when I run this. Same 6 segmentation fault happened, but let us examine what we have at address location 0x, no, this one now. When we look at this address location, we see C. C is what? 12. How many literals are we printing here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I removed the dash, that is why dash, and I removed an A. That is why it is not 14, it is 12. So this 12 things that we printed before this %4n is stored in this particular location 804 804A004. So now we can write things in this, but C points to some random place 000C. It is not system or it is not strdup. So when strdup happen, it crashes, right? When you try this strdup at global offset table, it crashes. So but we need to put some legitimate address here to get system. What is the legitimate address that we are going to give? We are going to give the address location of system. To get the address location of system, I will break at main. So even before the main starts, I break at main. So even before the main is called, it breaks. Okay, so I'll run the program. Start from beginning. Okay, I've run the program. Now I can see where exactly the function system is by printing p system. So address location where system is located is B7E5F4330. Okay, let me see if there are any messages. Maybe no. Okay, so this is the address location that we want. So over here, instead of C, if I can write this, we can make this thing work. We can make system get executed when strdup is trying to get executed. Okay, but how do we do this? We need to print random junk items which counts to B7E5F430 instead of C, right? So %10x, how do you do that? That's a simple thing. Again, our format string comes to our help. I have shown this in your manual. %10x, print of %10x, what it does is it print 10 elements. So it is a padding mechanism. I pad, if it is a x is like number 2, it will give 9 blank space and then a 2. Okay, so it pads up. So if I put %10x, it prints 10 literals. If I put %20x something, it makes sure that the number is printed in a beautiful way where there is 20 space, right? So we use this to print that much junk values instead of randomly typing in junk of this big size. But even then, B7 E5 for F430 is a large number. To print this, you'll probably have to, like, put a lot of space. It takes probably hours to finish printing that much space. Okay, so we don't want to wait that much long. We want to print it faster and get that much blank space, and then this value with %n goes in there. So how do we do this? We split this into two parts, the 2 bytes. B7 E5 has 2 bytes and F430 has 2 bytes. And to address location 804A004, we will put FX for 30. To 804006, we put B7 E5. So we split that into 2 parts. So instead of putting that 4 bytes at one go, we'll put the first 2 bytes first and then the next 2 bytes. So the first 2 bytes will go because it is little endian, the lowest 2 bytes will come first and the highest 2 bytes will come second. Okay, so to print F430, we need to print 62499. that is the number of bytes, because we already have 13 bytes printed because of sh semicolon hash. So this is 13 bytes, right? What is it? So this is 13 bytes, right? So that is there. With that, then we add with the dash, there's 13 bytes, and then F430, to reach F430, we need to add so much more bytes as well. So we'll put 64999, and instead of percentage for n, which is for the full 4 bytes, we can use hn. Hn is percentage hn basically writes 2 bytes. It consider the address location as a 2 byte, it's a short integer as a 2 byte value. So that 2 byte value will be stored in 804A04. Then the next 2 byte value, which is this much long, B7E5 minus F430, because F430 bytes are already been printed. So I only need to print 50101 to get a total of B7E5. 1 B7E5 will be stored. So 1 B7E5 basically means it is 3 byte long, but I can only store 2 bytes, and the lowest 2 bytes will be stored, that is B7E5. That will be stored at 0804A006. So this script over here, what it does is, it put sh semicolon hash and it gives this address location and then this address location. So this address location is stored in a stack which can be accessed by percentage for hn. This is stored in the stack which can be accessed by percentage 5hn. 5x basically will print it, and because it's for n, it will print all the elements that is printed, or total number of literals that is printed, that is 13 plus this value, that becomes f for 3 or whatever the number is, and that will be stored in this location. And this total number plus 5010, which is 1 B7E5, will be stored in 1 B7E5 will be stored in this location, but that one won't be stored because it is overflowing. B7E5 will be stored here. So at the end we have 0x, this location will have B, the address location that we wanted, which is where, this one, B7E5 F430 at 0804A004 will be having this one. Okay, so let us try running this. Now I need to remove all the breaks. This may not run because of the breakpoint. So clear all, clear breaks. Okay, I forgot the comment for that. So let us start again and then copy this. When I run this, You see all the space that happened. This is the number of like the space that we need to get that that number of elements. That's why I said, you know, this is after getting making it into 2 bytes. So imagine it's 4 byte, you know, it keep printing, you lose a lot of time just waiting to get the result. So I get the shell here because now system message is getting executed. Let us try again. Present working directory, see. So now even with data execution protection, we still get our shell. Questions? Okay, so I took another extra 10 minutes, even though I said I'll finish at 11:30. Sorry for that. So what we will do is I'll wait for some time if you have questions. If you don't, what we can do is during the afternoon lab session, you can call me into your breakout rooms and ask me doubts regarding this two either format string or buffer overflow attacks that we have seen. Does that make sense? I'll give a minute because there's a small delay in YouTube live. Give a minute to see if there are any specific questions and then let you leave. Okay, so thank you then. I don't think there are any more questions here, so I will see you guys in the afternoon. You can be a bit late, it's fine, because I took a bit of your time. We'll see you at 1:15 and all the best. Thank you for listening through.